Earth is the only rocky body in the inner solar system that has strong magnetic poles. But where did these poles come from? And what do they do? For various reasons, Earth is a unique planet in the solar system. First of all, Earth is the only planet with a breathable oxygen atmosphere, and in addition, it is covered with liquid water and is the only known life-hosting celestial body. One of the features we often overlook that makes our planet special is its strong magnetic poles. For example, your compass might be useless on Mars. But where do magnetic poles come from and what exactly do they do? To answer this question, we need to start our journey from the center of the Earth. The Earth's core is divided into two layers, the solid inner core and the molten outer metallic core. Both layers are a mixture of magnetic iron and nickel, with traces of other elements like oxygen, silicon, and sulfur. The inner core is like a brilliant marble, relatively dense and hot. However, the outer core is liquid and circulates around the solid mass with its convective currents. This constant convection creates the Earth's magnetic field. The heat from the inner core continuously reaches the outer core and interacts with materials that have cooled due to plate tectonic activity. This cycle causes convection and enhances a process known as the geodynamo, which generates the magnetic field. Other planets like Mars and Venus lack magnetic fields to some extent due to the absence of plate tectonics. Based on the available evidence, these planets probably once had self-sustaining geodynamo systems, but for unspecified reasons, they lost them. Mercury has a weak magnetic field, with a strength reaching only 1.1% of Earth's magnetic field, and it does not provide an adequate protective shield against solar radiation. With the flow of molten metal in the Earth's outer core, its movement and high iron content cause the Earth to act like a gigantic dipole magnet, with one negatively charged pole and one positively charged pole. About 80% of Earth's magnetic field is formed this way, but the remaining 20% is not dipolar. Rather, it consists of parallel bands of magnetic force. In some areas, this magnetic field behaves like weather patterns. Irregular patterns produce strange fragments of the magnetic field. Areas like the South Atlantic anomaly are large strips of the Atlantic Ocean where the intensity of Earth's magnetic field significantly decreases. According to researchers, the reason for the decrease in the magnetic field is the strange tectonic activities beneath the surface of Africa. Areas like the South Atlantic anomaly are highly intriguing, but for various concerning reasons. According to Joshua Finberg, a geologist at the University of Minnesota, the magnetosphere acts like a protective sunscreen, helping to prevent dangerous solar rays from hitting the Earth. In areas where the magnetosphere is weak, more rays penetrate the Earth, thereby increasing the incidence of skin cancer. Another concern is the impact of solar flares on satellites. Solar flares, also known as coronal mass ejections, can disable satellites and other spacecraft, causing devastating consequences for telecommunications, internet access, and GPS services in affected areas. The South Atlantic anomaly is likely 11 million years old and is associated with another magnetic phenomenon known as geomagnetic reversal. The history of Earth's magnetic field can be found in ancient lavas and seabed sediments. These types of rocks are rich in magnetic metal fragments, such as small pieces of iron, which rotate around themselves along the magnetic field lines. Scientists know from sedimentary records that the magnetic poles of our planet shift over time. Currently, the geographic North Pole is approximately 500 kilometers away from its magnetic equivalent. According to NASA, the poles suddenly flip approximately every 300,000 years, reversing the magnetic north and south. However, paleomagnetic records indicate that a complete pole reversal has not occurred for nearly 780,000 years. According to some researchers, this suggests that we are on the brink of a reversal, and the strength of the South Atlantic anomaly could indicate that the next reversal is imminent. If the poles are to reverse, the Earth's magnetic field will likely face a 20% reduction in strength for centuries. Such an event could disrupt current global communication systems. However, according to other studies, this reversal is not imminent. Anyway, studying the planet's interior and the ancient geomagnetic records help us understand the complex interaction between the magnetosphere and life on Earth, and also prepare us better for future changes. Thanks for watching the video, and don't forget to subscribe.